Up until this point, we have looked at graphs and position time graphs, velocity time graphs, acceleration time graphs, but we haven't quite looked at data tables. Data tables for us are usually showing us a trend, but for a position time data table, we see our position is increasing. However, it's very difficult to see whether or not that object is moving at a constant velocity, or it's getting faster as time goes on, or getting slower as time goes on, because your position could always be increasing while all three of those are happening. So a little bit of a reminder. Velocity itself is a change in position over a change in time. And an instantaneous velocity is talking about the velocity at a certain instant or time. Acceleration is defined as change in velocity during a certain time. And additionally, could be mathematically written as acceleration equals delta v over delta t, standing for change in velocity divided by change in time. Our velocity equation, if we remember, this is technically our average velocity for objects that are accelerating. So therefore, we can look at that velocity over a certain time interval, which would not be the same as each instantaneous velocity. Down here, it gives us a data table and then is asking us to find the direction of motion, the acceleration, the resulting motion description, sketch a position time graph, and a motion map. So to first do that, we are going to look at how this object is changing its position. We know it goes from a position at time 0 from 20 meters to 22 meters at time 1. If we look for the change in position, we can subtract final minus initial. And again, final is always talking about whatever instant you're looking at. So 22 meters minus 20 meters is 2 meters. I'm going to do this for each successive time unit. So 24 minus 22 is 2 meters, 26 minus 24 is 2 meters, and 28 minus 26 is 2 meters. This gives us the change in position, but if we are interested in looking at how the velocity changes, we would need to divide that by the change in time to get our velocity values. So if we can make a new column. To get our change in time, we have to look at the time intervals. We just used our change in position for, which was 0 to 1 second, so 1 minus 0 is 1 second. 2 minus 1 is 1 second, 3 minus 2 is 1 second, and 4 minus 3 is 1 second. If I go ahead and divide those changes in position, divide by that 1 second for each interval, I get a velocity of 2 meters per second, 2 meters per second, 2 meters per second, and 2 meters per second. So if I'm looking at the direction of motion, the sign of the velocity is what's going to answer that. Because these are all positive values, the direction of motion will be positive. The direction of acceleration is asking what the sign of acceleration would be. But if we have a velocity that is staying the same, assuming this is moving in the same direction, we have no acceleration in this case. And then as we look for what kind of resulting motion, the object is not getting faster or slower, staying at a constant velocity, and that constant velocity is 2 meters per second. For our sketch of a position time graph, we can look at our initial position is 20. We aren't sure where 20 is, but we can assume it's greater than a position of 0. So I'm going to start my position here. And then as I remember, on a position time graph, the slope means velocity. So I should draw something that has a constant slope of 2 meters per second. Because this is just a sketch, I don't need to have numbers on either side, again, not specifying our slope, but I know my slope should stay the same as I go on. If I were writing my motion map, I can put this as a position of 20 meters to have my first position marked with time equals 0 seconds. And then I can draw a velocity of 2 meters per second. At that point, we can talk about a motion for 4 seconds. So 1, 2, 3, 4. If I wanted to draw congruency marks, I could to show that those are all the same size. So that was for a constant velocity example, but moving to that next problem, I now can see it doesn't look exactly the same. We can do the same trend though and look for our change in position. So 2 minus 0 meters is 2, 6 minus 2 meters is 4 meters, 12 minus 6 meters is 6 meters, and 20 meters minus 12 meters is 8 meters. We notice we don't have a consistent change in position. This time our change in position is increasing as we go. So to look for the velocities at that time, we again will have to look at that change in time for each of them. They happen to be the same, 1, 2, 3, 4, so each change in time is 1 second. I can divide each of these by 1 second. And my values go to 2 meters per second, 4 meters per second, 6 meters per second, and 8 meters per second. So a couple things we can answer right now. My direction of motion, because these values are positive for my velocity, I am moving in the positive direction. As far as looking for my direction of acceleration, we now have to do that extra step and look at how much that velocity is changing in what amount of time. So first we can find the delta V, or the change in velocity. Looking between each of these velocities, I see 4 meters per second minus 2 gives me a value of 2 meters per second. 6 meters per second minus 4 meters per second gives me a value of 2 meters per second. 8 meters per second minus 6 meters per second gives me a value of 2 meters per second. But remember, this is just the change in the velocity. We have to look at the change in the time that occurred. And if we look on this side, we see each of those happened from 1 second. So if I divide this by 1 second, I can now show that I have a change in velocity over change in time, which is my acceleration, of 2 meters per second squared, 2 meters per second squared, and 2 meters per second squared. Because this value, my acceleration, is positive, my direction of acceleration is positive as well. As I see, my direction of motion and my direction of acceleration both being in the same direction will result in the object getting faster as time goes on. We could also see that through the fact that my velocities go from 2 to 4 to 6 to 8. The magnitudes of those speeds are getting larger. So 2 different ways to look at it. The fact that they're in the same direction, or the fact that magnitudes get larger. Looking at that on a position time graph, I do have a start of 0 for my position. And so when I'm drawing this, I need to look at my tangents. I need to draw something that has a low tangent to a steep tangent and in the positive direction. So this is a less steep tangent in the positive direction, more steep and steeper. So something like that. For our motion map, you would be looking at an initial position of 0. I'm still moving in the positive direction, and as I move in the positive direction, I will be getting faster. So with my velocity vectors getting larger each time, I need to show my acceleration in the positive direction that is causing that velocity to get larger. As far as times go, we aren't too concerned anymore with what these times are showing, since it's so hard to talk about the instantaneous velocities. So something around the time given is appropriate. Looking at the last problem, on the front side, we can see that the change in position, 40 meters minus 10 meters is 30 meters. 65 minus 40 is 25 meters. 85 minus 65 is 20 meters. And 100 minus 85 is 15 meters. So now our change in position is decreasing as time goes on. If we divide that by our change in time, which again each one is 1 second, then we find that our velocities would be 30 meters per second, 25 meters per second, 20 meters per second, and 15 meters per second. Because this is a positive velocity, my direction of motion is positive. Now before we answer our resulting motion, which you could answer at this point, let's take a look at how our velocity changes in a certain amount of time. So our change in velocity would be the difference by each of these. So 25 meters per second minus 30 meters per second will give me a value of negative 5 meters per second. 20 minus 25 is negative 5, and 15 minus 20 is negative 5 as well. Because the time increments between these two are 1 second each, I can divide by that 1 second, and my acceleration values are negative 5 meters per second squared, negative 5 meters per second squared, and negative 5 meters per second squared. Because this acceleration is negative, the direction of the acceleration is negative. These two being opposite will tell me that my resulting motion is getting slower. I could have also seen that by the fact that my velocities were decreasing in magnitude. So there's more than one way to look at it. Additionally, on our position time graph, we start at position of 10. We have a steep positive slope that goes to a less steep positive slope. So something like this would be an appropriate position time graph. On our motion map, we can put this as a position of 10, where time equals 0 seconds, and we have a large velocity that is going to decrease over time. That acceleration is going to be in the opposite direction, so for us to the left, showing why that is slowing down or getting slower as time goes on. You should be able to finish the ones on the back side of the sheet and notice that sometimes these negatives and positives are really important while you're doing that math.